Okay, so to begin, I'm just going to explain what oscillations mean. So essentially, oscillations in simple harmonic motion is just the So what this means is that, anything you can think about. In this case, I'm going to be explaining a swing set. So anything where we have the swing here, and we're just from the side, we're going to go back and forth. And right here, where these dots are, we call our equilibrium point. So something to think about is that something in a circle is also, so if you had a merry-go-round, the way to explain this is that I just have a circle like this, right? All that's happening here is simple harmonic motion in the x direction and simple harmonic motion in the y direction. All that's happening is that I'm going back and forth, and back and forth. Damped oscillators. So a damped oscillator is just where there's some frictional force that's proportional to the velocity, and the frictional force is said to be damping the oscillation. So here is the oscillator in simple harmonic motion. That's what the SHM stands for. And the x-axis there demonstrates the equilibrium point. And here we see that it's very uniform, whereas uniform is like a draw. And there's nothing changing. We have the same distance on the top as the bottom. But if I add a frictional force here, I'll get a damped oscillator, where we can see that as time goes on, I get less and less and less height from the axis, meaning that I'm able to go less and less further from the point of equilibrium. And I would demonstrate this with the swing. So here, with the swing, we have my little guy, and pretend that my hand pulling on this string is really a person. So in my damped oscillation, each time it's going to get less and less. And I want you to imagine that this pull right here is the point of equilibrium. So when I go, he will go back and forth, but over time, it gets shorter and shorter and shorter until he will eventually stop. And this is because in a real world, we have frictional forces acting on him, right? I mean, there are lots of things going on here. So each time the swing gets less and less distance from equilibrium, which is this pull. Okay, so moving on to critically damped oscillators, we explore a topic where we're going to apply a force to approach zero amplitude as fast as possible. But the idea here is that the approach to zero is actually our approach to equilibrium. So the main idea is that we're going to apply enough force to bring the swing back to equilibrium as fast as possible without ever really oscillating. So a diagram here is that my hand, which is going to act as the pusher on the swing, is actually really pulling the swing. So imagine if you were pushing somebody and you ran backwards and then ran forwards and just stopped. So here, when I do the demonstration, please understand that I can't control it exactly because I'm also videoing. So there might be a little oscillation at the end when I bring it back, but the idea is that it would stop right there. So I have this string here, and I'm going to pull up, and I'm pulling, pulling, pulling as it's going down, and then as fast as I can, I'm gonna go boop to equilibrium. All right, in our final topic with oscillations here, we have overdamped oscillators, which is where so much force will be applied that the object will reach equilibrium very slowly. So here I have drawn sort of a series of events. So here we will start. There will be a person pulling up the swing, and then as time goes on, they're going to be pulling up so hard that the swing will go back very slowly, and then at time 3, we have it back at equilibrium. So a good example here is if, say you had a baby on a swing and you wanted to pull up so hard so that the baby wouldn't come off at the end. You want to go very, very slowly, right? So here I will demonstrate this. So my hand acting like a person, I will pull up so hard that the person will go down very, very, very slowly. Just like that. Compared to the other one in the other video where they went back very quickly.